Good morning, everybody. Welcome back to stellar pulsation theory. In yesterday's tutorials, Professor Yadav has discussed both the virial theorem and the mass luminosity relation, and he has given a detailed derivation of both virial theorem and the mass luminosity relation. Since both the virial theorem and the mass luminosity relation are essential, very essential for our understanding of stellar evolution and stellar structure, I will comment on them today, or I will repeat some of the results he has derived yesterday, and I will discuss it in the framework of stellar evolution, how they are responsible for driving stellar evolution and what needs to be considered, what needs to be discussed in connection once these theorems are no longer valid. Okay, let's first turn to the virial theorem. Well, the virial theorem was derived on the basis of the equation of state of an ideal gas and the requirement of hydrostatic equilibrium. And we got the result that the gravitational energy is minus 2 times the thermal energy of the star. Where the gravitational energy, the gravitational potential energy, is given by the integral over the mass of the gravitational energy per mass, which is gmr over r, and the integral over the mass gives the total gravitational potential energy of the star. The thermal energy, on the other hand, may be expressed by the integral over the heat content, which in this case is written by the specific heat at constant volume times the temperature. So this is the heat. This is the heat per mass and Kelvin. So this is the CV times T is the content, thermal energy content per mass integrated over the mass gives the total thermal energy content. If you compare it to Professor Yadav's notation, you will find a small difference, but if you rewrite the pressure over density, which occurs in his derivation, then you will end up also with the formulation that is CV, which is usually 3 halves times the gas constant. This is something like P over rho. This is what's remaining. So we are essentially ending up with identical formulation. So it's just another way of rewriting the thermal energy. Okay. Well, the assumptions to arrive at this form of the virial theorem was hydrostatic equilibrium. Now we are dealing with two kinds of energy, the gravitational energy and the thermal energy. So sometimes the virial theorem is confused with the energy conservation because we are dealing with energies. But we have not adopted the energy equation. What we have adopted is hydrostatic equilibrium. So keep in mind, the virial theorem has nothing to do with energy conservation, even if it uses in its arguments or in the result, it uses two kinds of energies. So it's just a consequence of hydrostatic equilibrium. There's nothing to do with energy conservation. The second point is we have assumed the equation of state of an ideal gas, and actually the ideal gas is responsible for the factor 2 here. If we take another equation of state, we will end up with another factor here. It's also in general, if you can derive the virial theorem, then in general you will get a similar relation, but the factor in front of the thermal energy will not be the same. For instance, if we take pure radiation, then we will end up with a factor of -1 here. So keep in mind, hydrostatic equilibrium, no energy conservation is used, and we have used an equation of state of the ideal gas. So if we take another equation of state, we may end up with a similar form, but not with the factor of -2 here in front of the thermal energy. Okay, so virial theorem has nothing to do with energy conservation, and Professor Yadav already discussed the implications of the virial theorem in this form. Well, the first one is that the total energy, which is given by the sum of gravitational and thermal energy, is then given gravitational energy is -2 times the thermal energy is given by minus the thermal energy. Thermal energy is positive. So the total energy is negative, which means we have a gravitationally bound system. Well, then he considered, and I'm repeating this now because this is very, very important, and you have to go yourself possibly through this analysis again. Well, if we consider the contraction of the star, then we release gravitational energy. Why is that? Delta Eg is bigger than 0. Well, if we shrink our star, if we contract our star, the radius becomes smaller, so this becomes the modulus of this quantity becomes bigger, and therefore the gravitational energy becomes more negative. So delta Eg is negative once the star contracts. So it releases then gravitational energy once we contract our star. And according to the virial theorem, then the change of thermal energy is -1/2 times the change of the gravitational energy. And once minus delta Eg is bigger than 0, delta E thermal is bigger than 0. So the star becomes hotter. The thermal energy increases. At the same time, we have that the change of total energy is minus the change of the thermal energy. That is equal to, of course, according to virial theorem, is equal to 1/2 times the gravitational energy. This is then negative. So we have the fact or the result that a decrease of the total energy is always associated with an increase of the thermal energy. So this is a system which loses energy, or once it loses energy, then it becomes hotter. This is very counterintuitive. All systems we know on Earth show the opposite. If they radiate energy away, if they lose energy, they become colder, they do not become hotter. So total energy decreases. Decrease in total energy is associated with an increase of the thermal energy. This total energy, the decrease of total energy, of course, might be done simply by radiation of the star. And we saw once we went through this analysis, that half of the released gravitational energy goes into the radiation of the star, and the other half of the released energy is needed or used to make the star hotter, to increase the thermal energy. This is the result of the consideration we have had just before. So we have released the gravitational energy, half of it goes into thermal energy, and half of it goes into the total, goes into the radiation from the star. Okay, well, this question or the association of increase of thermal energy associated with an energy loss from the total system is usually addressed as a negative specific heat. We lose energy, and at the same time the star becomes hotter. Well, the question is, where does this come from? This is counterintuitive. This does not happen for any system we know, except for stars. There are other astronomical objects where this also takes place. So what is responsible? Where does it come from? The decrease of the total energy heats up the system. what is responsible, what do we usually not take into account, at least do not consider in the total system. It's gravity. So gravity is responsible for that strange behavior if we include it in our thermodynamic system. Of course, we could also regard the system only in a thermodynamic way. Then we would consider stellar matter as usual. But here we have explicitly taken into account gravity. And if we take both the thermodynamics and the gravity together, then we will end up with this strange behavior. So gravity, or the consideration of gravity, is the reason for this negative specific heat. I told you there are other astronomical systems where this exactly the same phenomenon happens. Gravity plays a major role. This is, for instance, in the dynamics of star clusters. If you consider a globular cluster and you if you get rid of energy in the globular cluster, then it will shrink and the velocities of the stars become higher. This is nothing else but increasing the temperature of the star cluster. That means the thermal or the kinetic energy of the stars increase once you reduce, or once you get rid of, or you extract energy from such a globular cluster. So it has exactly the same properties. You take out energy of this globular cluster and the velocity of the stars will increase, or in other words, the counterpart of thermal energy is the kinetic energy of the star cluster. Then the thermal energy will increase in such a star cluster. So gravity is always responsible for this strange behavior, that energy loss leads to an increase of temperatures or increase of kinetic energy in the case of a star cluster. Okay, so what we have, that loss of energy once the star lifts from its gravitational energy. So if it contracts, then the star leaves from this energy, is always correlated with the increase of the temperature during evolution. Actually, this is one of the driving factors for stellar evolution. This outcome of the virial theorem, or the implication of the virial theorem, that once the star loses energy, and it needs to lift from its gravitational energy, so it contracts, it releases gravitational energy, then this will automatically lead to an increase of temperature. Okay, this is one of the basic phenomena, basic issues of stellar evolution. The second issue, which has been discussed yesterday, is the mass-luminosity relation. What has been used to derive this mass-luminosity relation is also hydrostatic equilibrium, because our stars are in mechanical equilibrium, and we have used the equation of energy transport, which connects the luminosity of the star with the temperature gradient of the star. It's simple diffusion approximation. All diffusion approximation, or in all kinds or in all situations where you transport energy by some kind of diffusion process, you relate a temperature gradient to the flux. The bigger the temperature gradient is, the bigger will be the heat flux. So the energy transport has been connected with a hydrostatic equilibrium, and together with an equation of state, we have Professor Yadav has shown you that there is a relation between luminosity and mass. That means L, the luminosity, is fixed or determined by the mass only. There are no other parameters apart from opacity. Okay, there are minor effects, but from the main physical parameter of the star, there is only the mass left as a parameter of the luminosity. So the star's luminosity is completely determined by its mass. So if you have a star of a certain mass, you know it has to radiate at the rate which is prescribed by the mass luminosity relation. Once Professor Yadav has discussed the case when the equation of state is an ideal gas, and he has ended up with the relation between luminosity. Luminosity is proportional to the mass cubed. Well, this mass luminosity relation also depends a little bit on, well, not the existence of the mass luminosity relation. We always get a mass luminosity relation, but the exponent by which luminosity depends on mass, this depends a little bit on the equation of state you use. So if you use it as an equation of state, you take radiation pressure. Pressure is proportional to temperature to the fourth. You will end up with another luminosity mass relation, namely a linear relation between luminosity and mass. So if I may bother you with an additional exercise, simply take for exercise, take the pressure temperature relation P proportional to T to the fourth and redo or simply change a little bit the derivation you have seen yesterday given by Professor Yadav. Then you will see you will end up with the luminosity, a linear luminosity mass relation in that case. So, well, these considerations are based on a very crude estimate. Very crude estimates. We have replaced differentials. Simply dl by dm was replaced by L over m. This is a very, very crude way to estimate or to describe the properties of the system. So you may ask what happens to these relations once we do sophisticated stellar structure solve stellar structure equation, sophisticated stellar evolution theory. Well, the result is remarkably close to these relations. So what you find is if the stars have up to low mass or moderate mass, actually the luminosity is proportional to about mass cubed. The exponent is very close to 3 for low mass stars. And actually, if you go to high mass stars, you find that the exponent reduces to 1. So even this case, where you assume that the star is mainly supported by radiation pressure, is also seen once you do sophisticated stellar models. This is valid. The exponent 1, or the linear relation, is valid for massive stars. The reason being, well, massive stars are more supported by radiation pressure than by gas pressure. So this is quite reasonable that massive stars being supported by radiation pressure show the linear relation between luminosity and mass, which is close to the linear relation, whereas low mass stars or intermediate mass stars show the mass cubed dependence of the luminosity. So it's remarkably close to the exact results that in principle one cannot expect it to work that nice, but of course it supports our point of view that we have done the right physics. At least we don't get the numbers quite right, not exactly right, but we get results which are very close to the real values. Okay. Well, the essential point is this relation, luminosity-mass relation, is valid irrespective of any energy generation process. And now we can come back to our initial question, why does a star radiate? Well, the star has to, once we fix its mass, it has to radiate at a rate which is given by the mass luminosity relation. And what we have used is energy transport. So that means we have an energy flux because there is a temperature gradient. The energy transport relates the temperature gradient with the flux of the luminosity. And actually the luminosity is determined by the temperature gradient, or in other words, by the fact that the star is inside hotter than outside. There is a temperature gradient between the center and the surface, and therefore we have to have a flux. So the second question then would be, why do we have a higher temperature inside than outside? Well, this is then controlled by hydrostatic equilibrium. Hydrostatic equilibrium tells you that gravity balances the pressure gradient, and if gravity has to balance, or pressure gradient has to balance gravity, it's the other way around, then pressure gradient necessarily has to increase inward. This is a consequence of the hydrostatic equilibrium. Now, once you require the pressure to increase inward, if you have an ideal gas, then of course it could be done or could be provided by an increase of density. This actually is not sufficient. It needs, in addition, an increase of the temperature. So the pressure, the hydrostatic equilibrium, for the case of radiation pressure, it's immediately clear. You have a gradient of pressure. Pressure must be higher inside. If the pressure only depends on temperature, you have automatically a temperature gradient. Temperature has to rise from the surface to the center. In the case of ideal gases, you might argue that the density increase would be sufficient. It is actually not sufficient. That also lead to an increase of the temperature. So the reason, or well, energy transport is energy transport in the form that temperature gradient and luminosity have to be related together with the hydrostatic equilibrium, leads to this to the result that the star has to radiate at a rate which is given by mass luminosity relation. We haven't said anything about the energy generation. Nothing. So the question, why does a star radiate? Well, you can answer this. This is simply due to the fact that the star is hotter inside than outside. It's like a cup of coffee. Cup of coffee is hot, so the hotter than its surroundings. Well, surroundings usually cooler than the cup of coffee, so the cup of coffee will radiate because of its temperature difference. With respect to its surroundings. The same is true for the star. The question then, of course, arises, how does the energy generation come into play here? The star has to radiate because it's hotter inside than outside. This is controlled by the transport and the hydrostatic equilibrium. And the question is how the second point in the energy generation comes into play. Well, if the star has to radiate at a certain rate, then it has it's some kind of human phrasing. It has to look where to get this energy from. It has to see which energy sources are available to satisfy the prescribed luminosity. Luminosity is prescribed, and the star has to find an energy sources to satisfy or to fill in this luminosity which it has to radiate. Well, the energy sources a star can use, well, one energy source would be it contracts, then it can release gravitational energy, and it can satisfy then the prescribed luminosity mass relation by simply using its gravitational energy and by shrinking or contracting. Then it might satisfy this luminosity mass relation. Or if it's possible or if it's available, it can satisfy this relation by igniting nuclear burning and can satisfy this luminosity mass relation by powering this luminosity by nuclear energy release. These are the two sources which are available for a star. Okay. Well, I've already said star has to radiate at a rate prescribed by the luminosity mass relation, and the energy production within the star has to adjust to provide the required luminosity. So it can do it either by gravitational energy, by contraction, or it can be done by igniting nuclear processes. Okay. Second, well, if there are no nuclear energy sources, then the star has to rely on its gravitational energy. So if there are no nuclear processes are taking place, then it has to take its gravitational energy. So the star has to contract to release that gravitational energy and to feed the luminosity. As a consequence then, if the star contracts, now the virial theorem comes into play. If the star contracts and releases energy, half of it goes into the luminosity, which it has to feed, and the other half is used to increase the thermal energy. This is a consequence of the virial theorem. Then the star has to become hotter once it leaves from its gravitational energy. So now we have the combination of these two phenomena, mass-luminosity relation and the virial theorem. Well, what happens if the star becomes hotter? Then the temperature increase might lead to an ignition of the next nuclear burning stage. Yes?
So you explained that if the nuclear burning is not available, then the star has to rely on its gravitational energy.
Yes.
So this phenomena must be more dominant during the last stages of the star. Is it because when the star starts like dying, the nuclear fuel burns?
If this picture is correct until the end of the stellar evolution, then if it has arrived at the iron is the nucleus with the highest binding energy per nucleon, then there is no fusion, no exothermic fusion possible. Then it would have to live from its gravitational energy, and we would become hotter and hotter and hotter. So I wanted to ask this question later on, but now I can ask it because now I can ask you the question because you asked the question. Well, what will happen then if this picture is correct, and we have arrived at an iron core in the center of our star? No nuclear processes are available. Even if we heat up the star arbitrarily, there is no exothermic reaction. So the star contracts, releases energy. It still has to satisfy the luminosity mass relation. So how would we end up? What would be the pardon?
It will possibly contract and become more brighter or something like that.
Well, the brightness will not change. Luminosity mass relation. Well, what would happen? To simply describe the situation, it becomes hotter and hotter. There's a singularity in temperature. You cannot avoid a temperature singularity because the star has to radiate at this rate. It only has available the gravitational energy, so it shrinks and shrinks and shrinks, and the temperature goes to infinity. That's a strange situation, isn't it? Okay, but
the question that you asked, should this be analyzed using the hydrostatic equilibrium perspective?
Well, we have
in order to continue to be more in the equilibrium phase, it has to contract further, and whatever is radiated, something like that.
Yeah. Well, we have assumed, of course, hydrostatic equilibrium. Yes. This was the assumption. Given all these assumptions, we end up with a diverging temperature. If that's true. Well, let's stop perhaps at this situation and come back to this later on. May I ask you to wait for a few minutes and we come back to that question, because that is the question I wanted to ask at somewhat later stage. But it's good that you asked this question. But let me just explain some things before. Okay. Okay. So we have the situation then, how the stellar evolution will proceed. Well, there are two main ingredients. This is the virial theorem and the mass-luminosity relation. So stellar evolution, according to what we have seen now, it proceeds in the following scheme. Well, if the star let's start here at the left upper corner. Well, let's consider the star has had some burning phase and has powered its luminosity by nuclear reaction. So at some stage, the nuclear fuel will be exhausted, and it still has to power or satisfy his luminosity mass relation. So it has to take the energy, at least for some time, from the gravitational energy. So it has to release gravitational energy by contraction. Then it will become hotter according to Virel's theorem. The temperature will increase according to Virel's theorem. Well, the temperature increase then might lead to a temperature which is sufficient to ignite the next burning stage. We have seen the burning stages require successively higher temperatures. If we go from hydrogen burning to silicon burning, then the temperature increases because the Coulomb barrier of the reactions becomes higher and higher. So we ignite the next burning, and once the next burning is exhausted at some time, then the cycle goes on. Nuclear fuel is exhausted. The star releases again energy by contraction, then temperature increases with Virel's theorem, and so on. And this cycle continues for several times until, well, now we come to the question, what will be the final state of this evolution? Once we have reached iron as the ash of the last burning, then we would always go along this cycle, and we would end up with an infinite temperature as the final state of this evolution. Well, actually it doesn't take place. And what is the physical reason for this, for the fact that the cycle does not go on forever and do not reach infinite temperature? Well, some of our assumptions seem to fail. And the assumption that fails is that the equation of state is no longer that of an ideal gas. So the Virel theorem, keep in mind, was derived on the assumption that we have the equation of state of an ideal gas. So in the course of the evolution, this assumption will fail, and the Virel theorem is in its form given by Professor Yadav will no longer be valid. So the Virel theorem at some point of this kind of evolution will no longer be valid. We cannot apply it anymore. And this actually, Virel theorem is responsible for an increase of temperature once the star contracts. So this is no longer valid because the equation of state changes. Okay, so to understand that, let us consider what happens to the temperature as a function of density. In the course of evolution, the density will increase because the star only shrinks. So the star contracts, so the density will increase with time anyway. This is a byproduct of stellar evolution. But what happens? The question is then, what happens to the temperature? Temperature you would expect, if the Virel theorem is valid, would also increase with time. But is that really true? Question. Okay, so we consider a homologous contraction of the star with time. Homologous means this is an artificial construction, but it shows you in detail what really happens. Homologous means we keep the mass and the structure of the star constant. So the relative structure of the star is kept constant, and the quantities like density, pressure, temperature scale with the overall scaling factors, and we keep, in addition, during evolution, this is not a bad assumption, we keep the mass of our star constant. Let's illustrate what that means, homologous contraction. Well, we write the density or take an estimate of the density with the usual way. Density is mass over volume. The volume is proportional to r cubed for our star. So the density goes with mass over r cubed. If we differentiate this relation with time, and the time which we have in mind is now not the dynamical timescale is not the thermal timescale, it is the timescale of evolution, the timescale of contraction of the star. So the density changes by the change of radius. So if we take the density, the derivative of the density with respect to time, rho dot, and take the ratio of rho dot over rho, well, the mass is not changed, the mass is constant, then this is caused only by the change in radius. So we obtain rho dot over rho is minus 3, it's the exponent of this 1 over r cubed, minus 3 times r dot over r. Simply differentiating this relation, keeping the mass constant. Well, we do the same for hydrostatic equilibrium, where hydrostatic equilibrium is estimated the usual way. We have hydrostatic equilibrium, dp by dmr is minus gmr over 4 pi times the radius to the fourth. Now we estimate it in a very crude way. This is pressure over mass is proportional to m over r to the fourth, or pressure is proportional to mass cubed over r to the fourth. Now we keep the mass fixed and calculate the relative change or the change of the pressure with mass along such a homologous contraction. What we end up with is P dot over P, like the rho dot over rho, is then given by minus 4, this is the exponent here, times R dot over R. Okay, so we have used definition of density, we have used hydrostatic equilibrium, our star will be in hydrostatic equilibrium, and finally what we need is the equation of state. The equation of state is written in the usual form. We differentiate the equation of state. Rho is a function of pressure and temperature, and if we differentiate this relation, then we have rho dot over rho is d log rho by d log p at constant temperature. This is our famous coefficient alpha times p dot over t minus our famous coefficient delta d log rho by d log t at constant pressure times t dot over t. Okay, what do we do now? We can replace the what we are doing. What we want to do is we want to calculate the t dot over t in terms of rho dot over rho. So what we are doing is we replace r dot over r by rho dot over rho and insert p dot over p is then 4 over 3 times rho dot over rho, and insert this here for p dot over p. So it's a simple relation. Eliminate r dot over r, then we have p dot over p as a function of rho dot over rho, and we insert the p dot over p as a function of rho dot over rho here. Then we get a relation between t dot over t as a function of rho dot over rho. Okay, everybody satisfied? Okay, so what we end up with is t dot over t is proportional to rho dot over rho, and getting all these dimensionless factors here correctly, we are then left with t dot over t is 4 alpha minus 3 over 3 delta. So how the temperature changes with time in relation to rho dot over rho. Rho dot over rho is positive because density increases. Depends sensitively on the equation or on the coefficients of the equation of state, in particular on alpha and delta. Okay, now let's see what happens for an ideal gas. We are always starting with an ideal gas. So for an ideal gas, what is the value of alpha and delta? Okay. It's alpha and delta are equal to 1. once we consider an ideal gas, and this is the configuration we are going to start with. We start stellar evolution with an ideal gas. In that case, virial theorem is valid, anything is fine. So alpha and delta equal to 1. What do we get for t dot over t as a function of rho dot over rho? We get 4 times 1, 4 minus 3 is 1 over 3. So it's 1/3 times rho dot over rho. Or if we integrate this equation, that means t goes with rho to 1/3. Okay, if we integrate this equation, then we have t dot over t is 1/3 times rho dot over rho, and that means the temperature increases with the power t with the power 1/3. Ideal gas, the temperature increases like the density to 1/3. Okay, now I have to remind you of a result which we had at the end of the discussion of the equation of state. We considered the transition, once we considered the equation of state, we considered the transition of the equation of state from an ideal gas to a degenerate electron gas. So we introduced there the condition for degeneracy to happen is that the thermal energy of the particles is of the order kT. So kT, Boltzmann constant times temperature, this is the thermal energy of a particle, is small compared to the maximum energy which is reached once we fill all our electrons into potential pot, and this is the maximum energy which is reached once all particles, all electrons are completely filled in the pot, in the potential pot up to a certain maximum. So this has to be smaller than the maximum energy or the Fermi energy E0 or E0, which is the maximum energy of an electron in the basic or in the ground state for all electrons. And then we define on this basis the degree of degeneracy. Degree of degeneracy would be the ratio of this energy to the thermal energy. This might be regarded as a degree of degeneracy. If this ratio is big, then we are closer to degenerate. If this ratio becomes small, we are further off the state of degeneracy. So we may consider the ratio of K to KT over E0 or its inverse as a degree of degeneracy. Okay, so we have KT over E0 or its inverse is proportional to what we defined a degree of degeneracy. If we want to keep this degree of degeneracy constant, then the temperature has to be proportional to E0. So constant degeneracy would mean constant degree of degeneracy would mean that the temperature is proportional or goes with the maximum energy of or the Fermi energy of our particles. Now, how does this maximum energy depend on the momentum? Let's assume for the moment these are non-relativistic particles. Then the energy is proportional to P0 squared over 2m. So in that case, we have P0 squared over 2m. The m is not interesting for us, so we drop it here. The P0 depends on the number density of our electrons. We remember what is the dependence of the maximum momentum on the number density of our electrons. If we have a lot of electrons, we have, of course, we have to fill it to a higher momentum or a higher energy than in the case when we have a small number of electrons. Does anybody remember what we got there? Well, this P0 goes like number density of electrons to 1/3. Okay, so we have then this quantity goes like the number density of electrons to 2/3, because this has power 2. So if we have charge neutrality, then for each electron we have a nucleon. So this will be proportional to the density of our metal. So in that case, we would get T is proportional to the density to 2/3. So if we want to keep the degree of degeneracy constant, then the temperature has to rise with the density at least for constant degree of degeneracy exactly with rho to 2/3. If we want to stay in a non-degenerate state, then the temperature has to rise faster than rho to 2/3. Okay, now we consider these two cases. Well, for an ideal gas, we have that the temperature goes with rho to 1/3, and for constant degree of degeneracy, we would have the temperature to rise with rho to 2/3. So it has to rise faster than the temperature rises in the case of an ideal gas. What does it mean? Well, the degree of degeneracy, once we have an ideal gas and the star evolves, does not stay constant, but the degree of degeneracy increases, or the matter within the star becomes more and more degenerate. And finally, the final state, if it goes on, then the final state will be a state where the equation of state will be controlled by that of a degenerate electron gas. So we enter the domain of degeneracy, and finally we will end up with an equation of state of that of the non-relativistic degenerate electrons. Okay, well, what does it mean for the alphas in delta? Well, for non-relativistic electron gas, which will be this final state here, delta is 0. Well, we have P proportional to rho 5. Degeneracy means the pressure does only depend on density, and temperature drops out as a parameter. So the pressure goes like rho to 5/3 for a non-relativistic degenerate electron gas. So the alpha, which is d log rho by d log p, is 3/5 for non-relativistic electrons, and the temperature drops out as a parameter. So the derivative of the density with respect to temperature is 0. So once we have an ideal gas with alpha equals delta equals 1. Sorry, I don't get it on the same transparency. So we start with alpha equals delta equals 1. The temperature increase like rho to 1/3, enter the domain of degeneracy for electron gas. Then alpha varies from 1, this is the case of ideal gas, to 3/5, and delta varies from 1 to 0. What happens with our temperature? The change of temperature with respect to the change of the density. Well, what we see here is 1/3. This factor is 1/3 for the ideal gas. Now, let's have a look what happens. The denominator will change sign at which value of alpha? Alpha equals 3/4, then T dot over T is 0. So we have a change of sign. Usually we have an increase of temperature with density, but this may change the sign once alpha is 3/4, and we have seen alpha changes from 1 to 3/5, so it passes the position 3/4, so it becomes smaller, and this leads to the fact that T dot over T becomes negative, so that the temperature decreases with increasing density. This means we have a maximum temperature once we have a transition from ideal gas to a degenerate electron gas. Moreover, the delta goes to 0, so this will be a very steep dependence. Once we go to delta close to 0, then the temperature will decrease, but it will decrease with a very steep slope, because delta goes to 0. So keep in mind, for alpha bigger than 3/4, we have an increase of temperature with density, and for alpha smaller than 3/4, we have a decrease. That means we necessarily get, by this transition from an ideal gas to a degenerate gas, we automatically get a maximum in temperature. Temperature at some stage, once we reach degeneracy, will decrease with density. Okay? Okay, we have T dot over T bigger than 0 for alpha bigger than 3/4, and T dot over T smaller than 0 for alpha smaller than 3/4. Well, so in the case of degeneracy, the temperature decreases for contraction, and it means it achieves a maximum, and then the temperature is no longer become higher than this maximum. And as a consequence, if there is a temperature maximum and we are just in a stage between two possible burning phases, that means that the next burning stage possibly is not reached, and you cannot go through the next burning stage. Well, this helps with our strange situation which came up once we asked what happens if the virial theorem would be valid forever. Then we would get an infinite temperature. This is prevented here by the fact that the gas or the stellar matter becomes degenerate. So this quantum mechanic effect of degeneracy really influences on a macroscopic way. Degeneracy is usually thought to be a microscopic effect. Here it has macroscopic consequences, because this quantum mechanic effect of degeneracy prevents the star from getting infinite temperature. It prevents, or it is responsible for the fact that all stars, more or less, stars have, at least some stars, I will comment in a minute, that some stars will reach a maximum temperature and may only undergo several burning stages, and the later burning stages cannot be achieved because the temperature maximum is reached before the next burning stage will be ignited. Okay. So the higher burning stages will burning phases will not be reached if degeneracy sets in before that. Okay, the next consequence is there is a maximum temperature or maximum temperature during contraction and transition from the ideal gas to the degenerate electron gas. So the question arises, where does this temperature maximum actually, where the temperature maximum actually is achieved, and on which parameter this temperature maximum or the reaching of the temperature maximum is controlled. And here I have to, I cannot demonstrate this because this requires real stellar evolution calculations, but in a schematic way it looks like the following. So this is in a schematic way the run of the temperature with density. Here we have log central temperature against log central density, and the thick arrows are the tracks or are the lines along which the star evolves during stellar evolution. So if the mass is small, then this maximum occurs at a finite density. Temperature increases, then alpha becomes equal to 3/4. Then we have reached a maximum, and then we have a decrease in temperature. So we reach a maximum in temperature. If the mass is smaller, then this maximum is reached earlier. So for masses smaller than 0.1 solar masses, it's reached, particularly here, before the temperature of 10 to 7 K is reached. What does it mean for a 0.1 solar mass star? If this maximum due to transition to degeneracy is reached, before a temperature of 10 to 7 is achieved. This maximum occurs below temperature of 10 to 7 K. What is 10 to 7 K? Is this which nuclear fusion? It's hydrogen. Hydrogen fusion occurs around 1 times 10 to 7. So a star with mass smaller than 0.1 solar mass will not reach hydrogen burning. Well, it has to be bigger to reach hydrogen burning. Well, and then the next gap or the next domain or region of masses might not, if the mass is not massive enough to get a temperature of 10 to 8 degrees, it will not ignite helium. If it's more massive, then it might ignite helium, but not yet carbon. And so, well, you have a range of masses, and depending on the mass, you will not reach either helium burning, even not hydrogen burning, even not helium burning, or carbon burning, oxygen burning, magnesium burning, and you will stop the evolution due to degeneracy before some of these stages of burning are reached. Okay, this is an effect of degeneracy. Well, for very massive stars, here we have 10 solar mass star, well, this does not reach degeneracy, or it reaches degeneracy after silicon burning. In any case, it will reach degeneracy once it has done iron, once it has undergone silicon burning, because this is the last burning stage. Then the star has to contract, and once it contracts, it enters always the degeneracy regime. But this is no longer telling you whether the next burning stage is reached or not, because we have already undergone all the exothermic burning stages. So even in the case of a very massive star, we will in the end up with a degenerate iron core. This would be a star which is massive enough to undergo all the burning stages. If it's less massive, then the evolution may stop before silicon burning, or if the star is even less massive, then it will stop before oxygen burning, or even if it's very low mass, then it even stops before it reaches. It even stops before it comes to hydrogen burning. This is the case for masses below 0.1 solar mass. Okay, that's the evolution in the schematic way in the interior of the star. So the which stages of burning are reached depends on mass, and the final stages of stellar evolution will then will either be degenerate stars. So it's always degeneracy is always the final stage, or we end up with stars which have degenerate cores. Degenerate iron core, or the complete star, except for its envelope, is degenerate. These are the final stages of stellar evolution. In that way, degeneracy avoids this singularity in the temperature which would be present once the virial theorem would be valid until the end of stellar evolution. So degeneracy, quantum mechanical effect, is essential for stellar evolution. Okay. So in the end, what this tells us is we have to deal with degenerate stars, because that seems to be the only way a star can end its life. So let's go to the property of degenerate stars. Well, the equation of state of a degenerate gas is depending only on density. So we have a function. The pressure is then no longer a function of temperature. It is only a function of density. Now let's estimate in the usual, or shall I stop? Okay, then let's have a break.